So next, we're going to get into reaction stoichiometry. So a balanced equation relates the relative amounts of reactants and products at the atomic scale, as far as molecules, and at the macro scale, in terms of grams. So if we go back to our equation of methane reacting with oxygen to form carbon dioxide and water, on the atomic scale, we have one methane molecule reacting with two oxygen molecules to produce one copper dioxide molecule and two water molecules. If we multiply those by Avogadro's number, we end up with 1 mole of methane molecules reacting with 2 moles of copper molecules, 1 mole to produce 1 mole of carbon dioxide molecules and 2 moles of water molecules. And then, if we multiply each of those compounds by their molar mass, we find out that that is the same as saying we have a reaction of 16.04 grams of methane reacting with 64 grams of oxygen to produce 44 grams of carbon dioxide and 36 grams of water. So we went from the teeny tiny atomic scale to things you can measure on a balance. So in the lab, I am sure you remember measuring things that were in grams. You measured some water at one point, and you should have measured 5 or 10 grams of water. So these are on the order of magnitude you can measure on a balance, whereas these are the ones that you need to look at under a very powerful electron microscope. But the ratios are all the same. The relationship of the reactants and products are the same, whether you're on the atomic scale or the macro scale. So balanced equations are very powerful. And therefore, all of our stoichiometry problems must begin with a balanced equation. Your first step is always balance the equation. So I know stoichiometry sounds a little scary, but we're going to break it down really easy, I promise. So this is a reaction of propane with oxygen. So we are combusting propane instead. So C3H8 reacting with oxygen. And this is a balanced equation. So we can use the stoichiometric coefficients. We can use the stoichiometric coefficients from our balanced equation. This is a 1. It's not there, but it's a 1. This is a 4, a 3. So we have stoichiometric coefficients that will provide ratios of the relationships between reactants and products, or reactants and reactants, and products and products. So from our equation, we see that 1 mole of propane is related to 5 moles of oxygen, or 5 moles of oxygen is related to 1 mole of propane. So you flip it one way or the other. It's a conversion factor, just like the ones we learned with dimensional analysis. This is just a different kind of conversion factor. Just like molar mass is also a conversion factor. They are equal things on top and on bottom based on our chemical equation. So we can write these mole ratios for any reactant and product pair. So if we look at our equation again, we have 5 moles of oxygen gas, 5 oxygens, and 4 waters. So 4 moles of water. So we can make a mole ratio using any of our reactants and products, and that is just a conversion factor that we're going to use in all of our equations. So we can use the balanced equation like a recipe. So let's start making some sandwiches. This is something that you can do in your house right now if you have all of these ingredients. Or you can use different ingredients, make any kind of sandwich you'd like, or you can bake brownies, cookies, whatever. So use a recipe. So in my recipe, we're going to assume that a perfect BLT contains 2 slices of bread, 1 tomato slice, 3 leaves of lettuce, and 4 bacon strips. It's a lot of bacon for one sandwich, I know, but that's my perfect BLT recipe. In our kitchen right now, we have only 10 slices of bread, but we have tons of all of our other ingredients, so don't worry about those. So, how many perfect BLT sandwiches can we make with 10 slices of bread? You probably figured it out in your head already, but did you know that you did it using stoichiometry? No, probably not. So we're going to work it out step by step so that the steps look less intimidating when we're working with chemicals. All right, so what are our ingredient ratios? We talked about mole ratios when it came to chemical equations. So now what are our ingredient ratios in our recipe? We have 1 tomato slice for 2 slices of bread, or 3 lettuce leaves for 2 slices of bread, or 4 bacon strips for 2 slices of bread, and 1 perfect BLT for 2 slices of bread. So those are our ingredient ratios. Everything is related to bread because bread is the thing that we have the least of. So bread is what we're going to use to determine how many sandwiches we can make. So we want bread in all of our ingredient ratios. All right, so let's see what that gets us. If we have 10 slices of bread and we multiply by our ingredient ratio for BLTs, that means 10 slices of bread divided by 2 slices of bread gives us 5 perfect BLTs. So we can make 5 BLTs. You probably figured that out in your head, but you didn't realize that you were using the ingredient ratios. So how many of the other ingredients do we need? Just so we can set out our ingredients on the counter. 10 slices of bread times our ingredient ratio of tomatoes to bread tells us we need 5 tomato slices. 10 slices of bread times our ingredient ratio of lettuce and bread tells us we need 15 leaves of lettuce. And finally, 10 slices of bread times our ingredient ratio of bacon to bread tells us we need 20 bacon strips. So to make our 5 BLTs, we not only need our 10 pieces of bread, we also need 5 tomato slices, 15 lettuce leaves, and 20 bacon strips. So that was a stoichiometry problem using sandwiches. So now let's look at our steps and we'll get into a chemical example. So our steps are, first, you always want to balance the equation. So when you have a recipe, it's already balanced for you. Somebody else put together that recipe so that you know how to make whatever it is you're making. So you have to balance your equation if it's not given to you balanced so that you know how to assemble your recipe. Second, you want to convert the known mass of the reactant or product into moles. So our mole ratios always have to be used with moles. You can't multiply your number of grams of a reactant or product times a mole ratio because your units won't cancel out. You need to use moles and moles. All right, so once you have the moles of your known reactant or product, you use your balanced equation to set up the mole ratios, and you use the mole ratios to calculate the number of moles of whatever the question asks for, the desired reactant or product. So you use a mole ratio of what you have to what you want to get your desired reactant or product number of moles. And finally, if the problem wants you to go back to grams for your desired reactant or product, you convert from moles back to grams using the molar mass. So these steps use the molar mass, and this step uses the mole ratio. Those are your conversion factors for those steps. All right, let's practice. So let's make some fireworks. So it sounds exciting, right? Barium sulfate reacts with hydrochloric acid to form barium chloride. Barium chloride is an ingredient in green fireworks, and sulfuric acid is a byproduct of this reaction. So we have 20 grams of barium sulfate, and let's just assume we have a ton of hydrochloric acid. So we have 20 grams of barium sulfate. How much barium chloride do we get, and how much hydrochloric acid do we need from our supply of hydrochloric acid? So our first step is to balance the chemical equation. So we have barium sulfate reacting with hydrochloric acid. These were all given in the equation to create barium chloride. We're given in the problem, sorry, not the equation. And sulfuric acid. So if you wanted to, you could check to make sure that these are all proper compound formulas, but they were given in the question for you, so you can assume that they are. So barium sulfate is a solid. Hydrochloric acid is aqueous. Barium chloride is another solid. And sulfuric acid is also aqueous. So how do we want to balance this equation? I'm going to start with something that shows up in only one place, which in this case is everything. So barium, let's check barium. Barium is fine on both sides. Sulfur is fine on both sides. Oxygen, there's 4 of them in the sulfate ion, and there's 4 of them in sulfuric acid, so that's fine. What about hydrogen? So hydrogen, there's 2 of them in sulfuric acid, and only 1 of them in hydrochloric acid. So here's our first stoichiometric coefficient. We need to add in a 2 in front of hydrochloric acid. So now we have 2 hydrogens on both sides. And that didn't affect anything over here. So it didn't affect our barium, our sulfur, or our oxygen. But it did affect our chlorine. So now we have 2 chlorines on the left. And look at that, we have 2 chlorines on the right. So this is our best chemical equation. Barium sulfate plus 2HCl goes to barium chloride plus sulfuric acid. All right, so now we have our balanced equation. So let's convert the known mass of our reactant to moles. So our molar mass of barium sulfate is given here, and we have 20 grams of it. So we're going to take our 20 grams of barium sulfate and find out how many moles of barium sulfate we have. So you want to divide by the molar mass. So we put molar mass on the bottom, the number of moles on the top. So we invert our molar mass. Now grams cancel out, and we end up with 20 divided by 233.38 grams. So we end up with 0.0857 moles of barium sulfate. All right, so now we have moles of our known reactant. So let's move on. All right, so we're going to use our balanced equation. We have 2 hydrochloric acids and 1 of everything else to set up appropriate mole ratios. Sorry, these should be aqueous. Okay, so since barium sulfate is the thing we have, we want to have all of our mole ratios in terms of barium sulfate. So barium sulfate on the bottom and our other reactants and products on top. Okay, so now we're going to use those mole ratios to calculate the number of moles of the desired reactants or products. So our question wanted to know how much barium chloride we produce. So we're going to use our mole ratio of barium chloride to barium sulfate. So from step 2, we had 0.0857 moles of barium sulfate. And from step 3, we had 1 mole of barium chloride per 1 mole of barium sulfate. So a 1-to-1 ratio means that we are going to end up with 0.0857 moles of barium chloride. Cool. Our question also asked how much HCl we would need. So let's find out. So we had 0.0857 moles of barium sulfate, and our mole ratio for this is 2 moles of HCl per 1 mole of barium sulfate. Our HCl was the only thing that we had 2 of for everything else. So that means we have to multiply by 2. So we end up with 0.171 moles of HCl. But those are not numbers we can come up with in the lab, so we need to convert them to grams. So we're going to convert from moles back to grams. So our moles of barium chloride was 0.0857 moles of barium chloride. And our molar mass of barium chloride is 208.23 grams per mole. So we can cancel out our moles and end up with 17.84 grams of barium chloride is how much we produced. And how much HCl did we need? So we had 0.171 moles of HCl, and we multiplied by the molar mass of HCl, which is 36.46 grams per mole. Cancel out our moles, and we end up with 6.25 grams of HCl. So we needed to use 6.25 grams of HCl along with our 20.0 grams of barium sulfate to make our 17.84 grams of barium chloride, which we'll use in our fireworks. All right, so that's a stoichiometry problem for you. And this is the general setup for reaction stoichiometry. We convert from grams of A to moles of A. We multiply by 1 over the molar mass, and then we multiply by our mole ratios to convert to B. And if we have to go back to grams of B, we multiply by the molar mass of B. So this is our setup for reaction stoichiometry problems. All right, so next time we'll talk about limiting reagent problems, which are another version of stoichiometry problems. All right, I'll see you guys next time.